So good morning. I think it's good to start on time, which it is now. So these are the 2 days of reckoning, and you will hear presentations of 3 teams. Today of 2 teams and tomorrow of another team. Perhaps you know what the background of the problems that they are working on is, namely that we decided on it. When I say we, I mean a very large, 35 people sort of decided on the 3 themes, on the 3 tasks, and the people who are going to talk to you have been actually working through the spring about it, and now very intensively for the last 6 weeks. So without further ado, I give you Elmar Noeth, who's going to talk about vocal aging.
Thanks, Fred. Okay, good morning, everybody. Today, our team will talk about vocal aging explained by vocal tract modeling. Let me start out with the problem. We do know that a person's voice changes due to aging. Other conditions as well, like emotional conditions, pathologic conditions, and these changes can be short or long term. Knowledge about that change can have applications in things as wide as far apart as security, medical applications, speech technology, and we just look at it also just out of scientific curiosity. There is some physiological changes that are known, some are not known that much, but we do know the vocal tract is lengthening. We have a reduction of pulmonary function, ossification of the laryngeal cartilages, increased vocal stiffness, and reduced vocal fold closure. And these have these cause certain changes in the acoustic signal, like the F0, and this is a very old slide from 1944, where they showed that with the male speakers, the F0 goes up at a high age, and with the female, it slightly goes down. We have an increased F0 variability, slower speaking rate, greater noise in the signal, and lower formant frequencies. Now, all these findings are from the literature, and I must say sometimes they're contradictory, because it depends a lot of the speech material. Is it an isolated vowel that is used? Is it red speech? People, for instance, found out that the F0 of a certain age group changed over time. So women around 1945 spoke with a higher pitch than around 1990. So if you compare an 80-year-old with a 20-year-old from 1990, you have a different finding. So the findings are very different could be very different in the literature. The goals that we set out in the workshop was, first, we want to analyze the influence of age on speech, and we want to look for applications. So when we analyze it, we're going to look at how do humans do. We're going to try to find objective measurements for the changes. And one of the goals that we would also like to do is initiate research on longitudinal data, and I will explain that in a second. Data of one speaker over a longer time. The applications that we have is, could we have a age-related adaptation for improved automatic speech processing, and could we classify the age of a person from speech? The principal approach that we took is that we first say, well, let's look how the humans do. Then we try to look at robust features, that is, features that eventually can be used for speech processing. We don't want to depend on a very detailed hand time alignment, that kind of stuff. We want to examine the variability of automatically derived features. Can we really get them robust? Verified findings that we get on data from one speaker over a long time, on cross-sectional data that is many speakers that we take in at one point in time. We want to interpret these changes, and then the two real applications. Can we predict the age of a speaker based purely on a speech signal, and what can we learn for a speaker and speech recognition? So what we do is we go and we calculate features. These features could be standard MFCCs, formants, articulatory parameters, prosodic parameters, and so on. And then we take these features and we make a regression analysis with age. Is the change, is there a trend that correlates with age? We also use these features to predict the age with support vector regression. That is, we don't classify into young, middle-aged, old or so, but we predict, given the signal, what does the algorithm think, what does the support vector regression think is the age. Then we can calculate the mean absolute error between the chronological age and the predicted age. And we can also calculate a regression between the chronological age and this perceived or predicted age. If we want to do a classification that can be derived from that data just by taking that age and mapping it onto a class. So take the predicted age and mapping it onto a class. Let's say the person is older than 20 and younger than 30. Let me start now with an overview, and the points will be presented by different people of the team. I will start with introducing the data that we worked on and human performance. Then we go on the source signal, that is the excitation signal. We'll introduce a model that we implemented during the workshop and how we optimize the parameters of it. Then we'll present the work on the articulatory inversion, so the signal goes now into the vocal tract. What can we say about the vocal tract? We will explain other parameters that we use to predict the age, that is duration and other prosodic and acoustic features. Then present results on the age prediction, and then go and introduce the speech recognition in the context of aging, that is show the baseline system and talk about ways to adapt the signal to a speaker group. And finally end with an outlook and summary. So let me start with the first part, that is introduce the data. We have longitudinal data, that is data from a few speakers over a long time, and cross-sectional data, that is data from several speakers at a certain age, and that over many speakers. The longitudinal data, we use the Queen of England. She's born in 1926, and we have the Christmas broadcasts of 30 years over a period of 50 years. Each of the broadcasts is like 5 to 10 minutes, which gives us 2.5 hours of speech. We have Alistair Cook, who was born in 1908. He also, just as the Queen has as a language, the received pronunciation. However, since he lived in Manhattan for most of his life, he has slightly North American influences. It's very known for the longest lasting radio show ever, that was Letters from America. We have 30 recordings for the time between 1947 and 2003, each about 25 minutes, which gives us 10.5 hours of speech. Then we have cross-sectional data that we acquired from the University of Florida. It's the University of Florida Vocal Aging Database. The language is American English. The material, there's several materials we used. The rainbow passage, the grandfather passage, and the spin sentences. There is 150 speakers with 1,350 stimuli. These 150 speakers were carefully chosen. So we have 75 males, 75 females, and we have 25 out of these 75 from the age groups young, middle-aged, and old. And we have perceived age judgments. So here's some examples of the material. The rainbow and the grandfather passage are well known and used for things like accent studies. So when the sunlight strikes and the raindrops in the air, they act and so on. Grandfather, you wish to know all about my grandfather. Rainbow passage, 329 words. Grandfather passage, 135. And then the speech perception in noise sentences, there's several hundred. They all spoke the exact same, 16 of them. Things like he caught the fish in his net, or the beer drinkers raised their mugs. So semantically meaningful, but hard to predict sentences. There's a couple of advantages of this database, which was recorded between 2003 and 2007. It's the same text, so there is no influence for the language model that can influence the age, the results. It's read speech, so there's no variation in that. It's the same microphone, so the same channel. We don't have to worry about the channel. We have about 2 minutes per speaker, that is 5 hours, and it's balanced with respect to the age groups. Here the mean is 21 for the young speakers, between 18 and 29, for the middle age between 40 and 55, mean value 48, and the older speakers between 62 and 92 with an average of 79. And the perceived ages are available, which are the means of 40 estimates of 40 different persons. So when we compare with these results, keep in mind this is an average already, so this is definitely much, much better than an individual human being would rate the age.
Elmar, is there any reason why the actual age is not known?
Oh, it is known.
Oh, it is known. Okay.
It is, it is.
We just don't use that.
That's an additional information. Oh, we use the actual age. It's an additional information that we can use. So here you see the chronological or the actual age, and here you see the perceived age. And as you can see, humans are doing pretty good. We have a correlation of 0.95 and a mean absolute error of 9 years. But as I said, this was the average of 40 judgments, okay? This slide shows us how many speakers we have per year. So we have about, a little bit more than 2 on average. The highest one is 7 speakers. For some years we have only 1 speaker, and so on average we have about 2 speakers per year.
Elmar, if you just go back to the previous slide. So it also looks like for the humans the slope is a little less than 1. And the
Yes, yes, people tend to underestimate the age. Well,
you underestimate old speakers.
old speakers, and that's a finding that we also see in our own perception experiments.
So maybe there's a simple first order correction. So if somebody reports that they perceive the age to be 37, maybe there's a simple first order correction that you make it 35.
Yeah, it's that first order correction that gives a 95% correlation.
That's what I'm saying. So in other words, when you use it, you shouldn't use the perceived, you should use the corrected perceived.
Okay, just to summarize what we have for data, we have longitudinal data. This is the Queen, this is Alistair Cook, and we have cross-sectional data. These are the male and female speakers of the Florida database. This is the year when it was recorded, and this is the year of the person when he or she was recorded. So let's talk about human performance. Vocal aging explained by humans. Out of the 30 recordings, we took 10-second segments. We hand-selected them because we wanted no words that gave away things about the time, as the Falkland War or something like that. Each question involved a random pair of these recordings, and the people had to listen to 2 recordings, one to the left and one to the right, and answer 3 questions about these recordings. So we'll listen to the recordings.
I hope that Christmas will remind us all that it is not how we communicate, but what we communicate with each other that really matters. Wherever I went among people living in the busy industrial towns or on stations and farms of the far outback, I met newcomers who reminded me.
So 3 questions were increasing difficulty. The first one, is the person on the left older or younger speaker? By how many years? And can you estimate the age of the left speaker? I'll present the answers. The one on the left is younger by 13 years, and the one on the left was 57. When we looked at the demographics of people who took part in this test, we had a self-proclaimed English level of 1 being the best and 5 being the worst. What you can see here. The first language of most of them were German, which had to do with the setup. We wrote to our students, can you please take part of that test? The age distribution, of course, with that kind of stuff is a little bit unbalanced. Most of the people were quite young. Also the gender distribution, if you write to an engineering school, you'll find just a little bit less women. These results are from 110 participants. Not each of the participants judged each utterance. We had an opt-out session because just listening to 30 pairs of the Queen can be kind of nerving. So we see a similar trend as with the Florida database. With the young speakers, a little bit of an overestimation. With the older speakers, a little bit of the underestimation of the age. There's a correlation in the same range as the Florida database, about 0.94, and the mean absolute error is also 10 years, which is in the was 9 years for the Florida. Oh, sorry, that was the classification of the age differences. When it came to the estimation of the age, also in the same range, 0.93, mean absolute error 9 years, and again underestimation of the elder speakers. Is there bias in any subgroup? We looked at different subgroups like natives, non-natives, males, females, and we couldn't really find anything. Here's the result for the males and for the females with respect to the age difference.
This will be gender of the person judging, not
Yes, yes. Yeah, because it's the Queen, so. Yeah. And also with the age estimation, pretty much in the same range. So now what we did was we took the individual judgment and correlated it to the mean of the others. And what we can see is that there's some people who are not very good and not in high agreement, but most of the people are agree quite well with the mean of the other people. And so to conclude this part, we can say that the participants were actually quite good at classifying the age difference and somebody's actual age. They seem to underestimate older voices. No influencing factors such as gender, age, and language proficiency was found on this database. And the results are in agreement with the cross-sectional data. So these were on the Queen, so longitudinal data. On the cross-sectional data, where people had 0.95. We feel that this is a low manual effort way to collect perceptual data because you don't have people to come in, you don't need to pay people to. The website will stay open and we encourage everybody to take part in that test. So having introduced the data that we work on and how humans do, we will now start with our analysis. Georg Stemmer will introduce how a model of the excitation signal and try to apply that.
So we have, as you see in this picture, we have the airflow coming from the lungs, and we have the larynx, which then modulates the airflow, and this signal is then, the source signal is then filtered by the vocal tract. And for modal voicing, we have a periodic opening and closing of the vocal folds, which are located inside the larynx. This can be illustrated on this picture. You see periodic opening and closing. There's a cross-section of the vocal folds. Airflow is coming here from south, going to north on this picture. And in the beginning, they are closed, and then they're opening and closing again. It is known from the literature that the larynx and the vocal folds are affected by aging. So we have cartilage, ossification, stiffness of the vocal folds, changes with age, and we have a reduction of in the closure. The goal of our work was to analyze age-related changes in the excitation function, and we specifically wanted to go beyond this obvious age-correlated pitch, which has already been shown several times in the literature. So our approach was to represent the vocal folds by a parametric model. And so going from the real vocal folds to some model of the vocal folds, and then to perform glottis inversion, determining the model parameters directly from the speech signal. And finally, we analyze the changes of these parameter values over age. And my talk just will cover the first point, introducing the models and its model and its parameters, and the second and third point will be covered by the subsequent talk of Andrew Cassidy.
John, before you go on, let me clarify something about what you consider a known result. You say that the pitch goes down with age for females and goes down when for males. Now, is this a longitudinal result, meaning for a given person it does this, right? In other words, if I simply gave you someone's pitch, you
we don't know its absolute pitch, of course. Yeah.
And then you can just say this is to the left
Yeah.
and right with time.
Yeah.
Okay.
Yeah, but even if you have a sample of speakers large enough, in average, I think the older speakers will have a lower pitch, of course, than the younger speakers, for instance. So a statistical correlation even is speaker independent, but yeah.
The variance between speakers, how does that compare to the difference between the same speaker at two ages?
I cannot answer this, I think so. Yeah, which vocal fold model the vocal fold model we implemented has been introduced by Kenneth Stevens long time ago. It's a very simple two-mass model. You can see we have for the vocal fold we have a large mass for the lower part of the vocal fold and a small mass for the upper part of the vocal folds, and they are connected by springs. Why did we decide to use this model? It's first of all, it has physically meaningful parameters. So the parameters do not just describe the shape of the excitation function, but really a physical property. And it has just very few parameters, so it's suitable for a data-driven optimization. And finally, we assumed from the literature that this model is flexible enough to express different voice qualities. And of course, the risk which we were taking here was that the complex changes due to aging could not be represented by this model, but as you will see later in the results presented in Andrew's talk, we were able to show that there are indeed strong correlations with aging and the model parameters. So how is the excitation function computed with the model by Stevens? It's computed in 3 steps. We have, first of all, we compute the displacements of the two masses over time. Then from these displacements, we can derive the width of the glottal opening. And finally, the derivative of the glottal airflow, which is the excitation function we can then use for our resynthesis, is computed out of this glottal opening. So we have several parameters determining the following curve over time. The blue curve is the displacement of the larger mass, and the curve below it is the displacement of the small mass, and the glottal width, so the width of the opening of the glottis, is then characterized by the red region here. So only here the glottis is really open. All of the rest, the glottis is closed. So you see the lower mass opens, and finally, due to the connection of by the springs, also the smaller mass opens. And when both masses are open, there's an airflow through the glottis. From this area of the glottal opening, we can derive the excitation function. It's simply the derivative of this, and this volume velocity is determined by further parameters, which are, for instance, the length of the glottis and also the acoustic mass of the air in the airways, which is larger when the vocal tract is more constricted. And we introduced, therefore, a skewness parameter phi of this volume velocity function. And of course, there are other parameters like viscosity, pressure, which we did not optimize in our model. So to summarize, we have 8 different parameters to optimize. We have the two masses, we have compliances of the two masses, and we have the resting position of the lower part of the vocal fold. We have the average vertical length of the lower part of the vocal folds, we have the length of the glottis, and we have this skewness phi of the volume velocity function. When we vary these parameters, we alter the shape and the frequency of the excitation signal. You can see here an example. In black, you have the default parameter settings for a male speaker residing in a pitch of 120 hertz. And if we reduce the compliances in masses, we get a higher pitch. Please keep in mind that masses here and compliances are masses per unit length and compliances per unit length. So they may be changed when the glottis is, when the vocal folds, for instance, are stretched. So it's not the absolute mass which is reduced, which cannot be reduced, of course. So how do we resynthesize the speech signal? We take an original speech signal, for instance, by the Queen, and we perform a linear prediction analysis on this, giving us LPC coefficients in a residual by inverse filtering with these LPC coefficients. Then we also apply a pitch extraction, and if the pitch is greater than 0, we synthesize the excitation function with our model in an optimization procedure which will be described in the next talk by Andrew. And the synthesized excitation signal is then filtered again with the LPC coefficients, which represent, in our case, somehow the vocal tract, and we get a new speech signal. For the unvoiced parts of the speech signal, we simply use the LPC residual. So I have finally, to conclude, I've got some examples. So this is an example of modal voice speaking.
Learning to speak well is an important and fruitful task.
And this is resynthesized by our model.
Learning to speak well is an important and fruitful task.
So you hear, of course, a difference, but it's much better than, for instance, if I use simply impulses as an excitation function.
Learning to speak well is an important and fruitful task.
Then there's another example of creaky voice.
Learning to speak well is an important and fruitful task.
And synthesized by our model.
Learning to speak well is an important and fruitful task.
And falsetto, which is the...
Learning to speak well is an important and fruitful task.
And our model can do it the same.
Learning to speak well is an important and fruitful task.
So I hope I was able to show that our model is able at least to represent a lot of different speech qualities. But now, yeah.
Just a question before you go. Just to make sure we understand, this resynthesis is just for your own edification, just to listen and see. The interesting part is what happened in the box there, and they're not going to use the resynthesized speech signals. Right?
Exactly. So the interesting part for us is, of course, just this excitation function. This is just to control if it really sounds good and so on. And this box will now be covered by Andrew's talk.
Here, just a quick question. To further validate that you're getting the right pitch, would it make sense to synthesize, let's say, the creaky voice with the glottal pulse sequence of the falsetto and see what it sounds? I mean, of course, utterance level difference.
Well, the pitch is already one part of our optimization algorithm.
Okay.
I mean, we optimize to get the right pitch. The main point of our work is not to get the pitch right, because we can extract the pitch with a pitch extraction algorithm. The point for us is to get the quality right, the shape of the excitation function.
Oh, I see. So the focus is not on the pitch.
The focus is exactly on all aspects which are not already covered by the pitch. All aspects of the excitation which are not covered. For instance, like creaky voice, which is more than just a low pitch.
I see. Okay. So then, no, I don't know this.
Okay, because then it would be very simple. We would take a pitch extraction, we have a clear correlation with age, and we are finished. We wanted to know more. So.
Was subglottal pressure one of the parameters?
Yes, we made an attempt to optimize it, but the model just changed it a very little, so we kept it constant now in all experiments which are shown below.
So just to add on to the last question, basically we're trying to optimize the excitation function without changing the pitch. So basically, we'll have a constant pitch, and we want to do everything we can to vary the shape of it without varying the pitch. And this is important, so it's a good question. It's a very good question. Okay, so good morning, everyone. My portion of the talk is talking about optimizing the GLaDOS model. So we have this hypothesis that the GLaDOS model parameters contain information about speaker age. So in order to test this hypothesis, what we want to do is find the optimal model parameters to fit the speech data and observe how they change with age. So our basic methodology excuse me, is to take 25 millisecond frames of speech and then optimize the parameters of the model to generate a source signal, and then see how that source signal matches the target, the original signal, and then observe how the optimal parameters, after we've done this optimization, change over age. As we said, as we've mentioned, we'll do this for a single pitch. So we want to try to find pitch invariant features. What we will do is we will take the parameters for a single pitch over all ages and then do our analysis. So here's our optimization loop. We have up here our excitation model, the model. We have the parameters that Georg described. And then down here we have the original LPC coefficients and residue. Then for each of these two models, we take a 25 millisecond frame every 10 milliseconds. And we have the excitation function that's generated by the set of parameters. Then we take that and we compute the log spectrum of that 25 millisecond frame. Then with the log spectrum, we can do a comparison between the original and the generated model. We do the comparison, it's Euclidean distance between the two spectrums to see the basic shape of the spectrum and also the pitch. So as we optimize it, we make sure that we do not deviate from the original pitch. We then take this distance measure and we feed it into an optimization algorithm. And so now you can see we have an optimization loop here where, given the data, we're able to minimize the distance and find the optimal parameters that fit the data. We looked at two different optimization algorithms, simplex algorithm and simulated annealing. The simplex algorithm is based on gradient descent. It does a local parametric search. Because it does just a local search, it is susceptible to local minima. So we also tried a second algorithm, simulated annealing. It's based on stochastic search. It has the ability to go up a gradient as well as down. So theoretically, it should find the global optimum and is not as susceptible to local minima. So here's an example of the excitation signal optimization. So this here, this is the log spectrum, and there's text missing from my slides. So in blue, what you can see is the log spectrum computed from the LPC. So this is our original spectrum. This is what we're trying to match. And in red, we have the GLaDOS model. So this is the initial condition. So these are the default parameters. This is the log spectrum that is generated by the GLaDOS model using default parameters. You can see there's not a very close match. So after 1,000 cycles of iteration, you can see here is the optimized result. So we've optimized the GLaDOS model parameters, and here's the spectrum. You can see the pitch has a very good match. In the higher order harmonics, we don't have an exact match, but we approximate the shape of the spectrum very well. So once again, to reiterate, we want to do pitch invariant analysis. So we looked at the pitch of the two speakers, and the two corpora we used were the Queen and Cook. And so what we did is we looked at all the speech in those two corpora, and we determined how often they used a certain pitch. So just a simple histogram here. So you can see the maximum here is about 210 hertz, and the maximum here is, I think, in the neighborhood of 90 hertz. So basically, that was that optimum, or that pitch that was used most frequently. That was the pitch that we did our analysis on in terms of the parameters. So here are the results for the Queen corpora. In the table, what we have is basically correlation between the model parameters and the age. In the top row, we have each of our 8 model parameters. We did the analysis at pitch value of 225 hertz, a little region in there, plus or minus 10 hertz. So we took all of the 25 millisecond frames that had a pitch of this value and did our analysis. So you see, and then in the 2 rows, we have the simplex algorithm and the simulated annealing algorithm. So you can see kind of a wide range of correlations. Correlations greater than 0.45, which are somewhat correlated, are shown in red. I took one of the better examples, mass 2, M2, and plotted it below. So you can see the 2 plots below. Looking at them, this one here is simplex. That one there is simulated annealing. Again, my labels aren't showing up. Anyway, you can see the data, there's a lot of variance here. You can see in the red line is a linear regression line. So you can see there is a basic trend, but the data is very noisy. So you can't say that, obviously the correlation is not that high, but you can see a basic trend. So with the Cook corpus, we found a much stronger trend. Here again, you can see this is the simplex algorithm and the simulated annealing. You can see they both come up with the same results, 2 different algorithms. You can see that doing simple linear correlation across the entire age doesn't make sense anymore because you kind of have this inverted V effect. Okay, so we broke the correlation up into 2 segments. You have the segment when he's younger than 80 years old, segment when he's older than 80 years old, and you can see the correlations above. So you can see in this case, we have very strong correlations. Correlations greater than 0.75 are in red. So particularly with these first 3 parameters, M1, M2, and C1, you can see very strong correlation, very strong. So we're able to see the strong correlation between these model parameters extracted by our optimization procedure and the age of the speaker. So finally, we took this and we did an age prediction. Sure.
Do you know if something happened to Cook in age 78? Or?
I don't know if there's anyone.
Because it's sort of,
He had cancer, lung cancer at some point, but we don't know when it started.
Not in, yeah, but not in 2000 something, right?
When he died, but
Yeah.
we don't.
Well, normally lung cancer is going fast. So.
It also is, I mean, just an observation that with elder men, you know, it seems like the change in the F0 is kind of fast. You know, like you out of a sudden you hear that somebody speaks with a higher pitch.
so this is sort of, I guess something happens at puberty at 13 or 14 to boys.
Yeah.
And then something.
Like something happens at 80 again.
I wouldn't say that 80 is, that's probably person dependent.
But we did see the kind of the U and kind of in earlier data, and we'll see it again, kind of these things happening as you're starting into the older ages of males. Yeah.
So at each age, did you have a good number of samples at this pitch?
Absolutely. So we only analyzed if we had greater than 1,000 samples, and so we're often in the tens of thousands, I think.
I think this was a problem for the clean data, that the correlations are not so high for the clean because we have much less data for the clean.
Right. So I didn't point it out, but there's about 4 times, so 10.5 hours, about 4 times more as much data as the queen data. So we think this is one of the reasons for the better results. Yeah. Okay, so finally we ran an age prediction experiment. This experimental setup used support vector regression. So support vector regression experiments can be talked later on by Werner and Young. So I won't talk too much about the experimental setup or methodology. I just want to present the results here. So once again, we have our hypothesis, and in this case, we're using the University of Florida database. So it's cross-sectional data instead of longitudinal. And what we did is we took then our resynthesized excitation signal. So basically took the optimal parameters, resynthesized them, and then took the MFCCs of that resynthesized signal. The MFCCs then we put into support vector regression. So you can see as our baseline here, we use F0 and the first 3 formants as our baseline. So this is not our model parameters. And then the next 2 columns are our glottal parameters. And the final column is a mix of the baseline plus the MOCs of our glottal parameters. So you can see for males, you can see the correlation is steadily increasing as we improve the model. With females, you can see there is kind of good correlation. You can't really say there's much of an increase there, but you can see that even just with our glottal model parameters, there's very good correlation, very good performance, and low mean absolute error. So once again, more evidence that we can extract using this glottis model correlation between age from the recorded speech. So that's my conclusion. What we set out to do, we think we've shown some evidence of this. And next up is Blaze. So in a source filter model, we have talked, Georg and I have talked about the source, and Blaze is going to talk about the vocal tract.
Quick question.
Sure.
Did you do the optimization independently for each frame, or somehow there was?
Yes.
Why didn't you consider a correlation between the frames? I mean, theoretically, you shouldn't change the parameters from frame to frame, right? Because it's the same person who is speaking. I don't understand why you consider independent optimizations for each frame.
Right. So
Pitch changes for each frame. Sorry.
All right.
To get a different pitch, you manipulate already the masses and the compliances of this model. This is part of the model.
But this is supposed to be constant, right? All these
No.
masses and this frame.
No. It's mass per unit length and compliance per unit length. So, for instance, you stretch something, you change some muscles, and then something becomes thinner, then you have a higher stiffness per unit length, so a lower compliance per unit length, and also a different mass per unit length. If some tissue becomes thinner, you have lower mass per unit length.
So you have lots of parameters essentially that you need to learn.
We have these 8 parameters, and they
8, but they change with time.
They
It's
change
not just a single
8 times time frames.
8 per time frame.
8 per time frame.
Yeah.
So you have, I mean, if you consider a supervector, it is a really huge supervector. And how can you correlate age with just one single? You take the average
Yes.
of all of them? You take the average?
Yes. So we've taken the average of at pitch 225 hertz, we take the average of all the parameters, and at that particular age, then you're at each age we will get a different average, and that is what we try to correlate.
From frame to frame, do you have big changes in the parameters that you optimize? Have you observed them?
They are pitch related, of course, these changes.
But you don't see lots of change from one frame to the other, so theoretically the optimized parameters shouldn't change that much.
If the pitch is constant, no.
I mean, it would be.
If the pitch is constant, are the parameters variable? Do they vary a lot, or is it pretty steady?
No, I don't have an analysis, an invariance analysis to say that in general.
But if they would vary randomly for a constant pitch, you wouldn't see these correlations. And as we saw them, there's at least some common mean to these parameters for a certain pitch value and a certain age.
Okay.
I mean, this is a difficulty that these parameters vary not only with age, but also with pitch. And that's why we took this pitch-dependent analysis. We only looked at a certain pitch.
So for Alistair Cook, it was just 90 hertz, and for the Queen,
Yeah, exactly,
it was
225.
the most frames
Yeah.
at a certain pitch.
All right.
And to be honest with you, that's actually the approach that we first took. They won't change at all. It took all the speech data and we had miserable results.
Oh, I see. Okay.
So-
That's an interesting.
Yeah.
Okay. All right.
Andrew?
Okay, good morning everyone. I'm Blaise Potal. I'm going to talk about the intuitive notion of articulation. What we wanted to, as Elmar mentioned before, we suspect that when we age, the articulation of the speaker is changing. So we wanted to study how the articulation of a speaker is changing over age. but mainly we don't really have articulatory data for a speaker over a long period of time. So what we do here is just try to study articulation from the speech. This is called articulatory inversion, acoustic to articulatory inversion. So basically, this is a short introduction of the problem. Acoustic to articulatory inversion is a problem because basically from one acoustic feature you can find several vocal tract shapes that will produce exactly the same acoustic signal. And also it's a very complex mapping to go from the speech to the vocal tract shape, because that's exactly what we want to have. And we want to do that because we really want to see how articulation change over age, using only the speak signal, because that's basically the only thing we really have. And we also want to provide a framework to generate features from the speak signal, which would be both channel and source independent. So independent from the glottis excitation and independent from the channel, like the type of microphone used. So for that we used an articulatory model, which is Maeda's articulatory model, which is quite famous. It was derived from X-ray from one speaker using X-ray sinoradiography. So we have many X-ray images, and we do a factor analysis was done on this. And from this factor analysis, 7 parameters were derived that are supposed to predict every possible vocal tract shapes. And it's only a 2D sagittal slice so basically it's only a slice like that of the vocal tract shape. And it is controlled by 7 deformation. It has 7 deformation modes. And it is quite easy to adapt to different speakers, which is a good point, but sadly it cannot really model consonant or nasalized vowels, since it's only the vocal tract shape, and there is no nose here. And it is quite simplified, so as you can see, a real vocal tract shape is much more complex. Here we only have a 2D slice, which is already simplified. So don't really have a very perfect geometric and acoustic faithfulness. And this is a brief description of the 7 parameters that control the model. The first one is that we call P1, is a model that controls the jaw, how you move the jaw. And there are 3 parameters, P2, P3, and P4, that control basically how the tongue is. The nice thing about this model is that almost every parameter has a physiological explanation. Like, for example, P2 is really the tongue position, so back or front, and P3 is the tongue shape. And we also have 2 parameters for the lips, P5 and P6, so the vertical opening and the protrusion of the lips. And we have 1 for the larynx. And what we expect to find when we the larynx was important for us because we expected to see lengthening of the larynx. And how do we, from a speak signal, how do we get these parameters? So it takes 3 steps. So basically, from each speak sample, for each speak frame, we get an acoustic feature. In our case, it would be the formant. I will explain later why we choose that. And for each for each frame, we generate many candidate solutions that will produce this acoustic signal. And then from this set of solutions that we generate at each time frame, we'll find a trajectory that will optimize an articulatory cause function using dynamic programming. And then we will smooth this this articulatory trajectory using the synthesizer to have a better acoustic precision and articulatory regularity using variational regulation. So I will just show an example how it works. So the first step is to extract some acoustic features. In our case, we choose a format because we suspect that they are the most, actually we took only the format frequencies, because we suspect they are the most independent of the channel and that they really are, well, everyone knows that it's probably the most important feature to discriminate vowels, at least for the human ear. So, well, anyway, here we use a software that automatically extracts the formants, and it's here 5 formats are displayed, but actually we're only using the first 3 because there are only those 3, the only formant frequencies that we can extract reliably from the speak signal. And then, for each of this time frame, we just generate, using a table lookup procedure, every possible solution that will generate the correct 3 formant. So F1, F2, and F3. So since the acoustic vector is very small, we can generate many solutions. So basically, here it's, so this is the time in milliseconds, and this is what the solution for one display for one parameter. So we project every articulatory vector on one parameter. So this is a lip opening parameter, and so we have many solutions for each time frame. But when we minimize the articulatory cost function, so basically we try to minimize the movement of the articulators, we realize that there is only, well, we can't find a best solution, which is still not very regular because we only use a discrete set of solution. And then we can smooth it a little bit. It doesn't look much smoother, but actually it has a better acoustic precision. And then in this case, we had the original articulatory data. And in this experiment, we had a very good, well, at least for this parameter, we had a perfect, almost a perfect match. So this is the actual articulatory trajectory. So in some cases, we get very good results. And we can expect that the vocal tract shapes that we find are very close to the original, at least for the vowels. And so we use this procedure on the Queen, and also on other point, but I will present some results on the Queen. So basically, from 16 acoustic features are extracted, so the 3 first formant frequencies, and from these features we compute the articulatory parameters P1 and P7. And actually, the first thing we did, just to check that we get at least something close from the original. So if we use these parameters, we have vocal tract shape, so we can, and if we use a glottis excitation, we can generate, so we should be able to generate the original signal, at least something close from it. And so this is, so I extracted a sentence over years, a sentence that the Queen says repeatedly, so for different years. Oh yeah, sorry. And this is a sentence every year.
Every year, 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 every year.
So if you pay close attention, you can see that the channel is changing quite a lot over the years, and also we can hear the aging of the Queen. And now the recent size signal. So we just take we take the original F0 frequency, but that's only thing we keep from the excitation. So
Every year, 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 every year.
Well, it's not very perfect. And the first thing that we see, you probably have realized that we don't hear the aging as much as the previous recording. But so it's not a very good sign, right? But still, we did some statistics on the So we can do some statistic on the very basic statistic on the articulatory vectors that we find. And the first experiment we did is just compute the average value of one parameter. So for every year we just, well actually for every sentence of the queen, we just compute the average values of the parameters. So this one is the Joe parameters P1. And what we can see is a nice trend. Actually, we see that these parameters is increasing over the years, which is, so apparently there are still some information, well, some indication about aging in these parameters. Well, actually, yeah, it's not very clear, but when P1 is increasing, that means that the jaw is closing. So that means that the average value of P1 is decreasing. Well, the average opening of the jaw is decreasing, which probably means that she doesn't open as much when she talks. And actually, sorry?
Why is this related to age?
That's a good question. But that's what we observe for the queen. So when you hear her speak, probably she's much more dynamical when she speaks when she's younger. She puts more emphasis but
more centralized articulation.
Yeah.
You just don't go to the extremes as much anymore.
Yeah. So this is an interpretation that we can give about that. And if we observe the standard deviation, so the amplitude of the movement for these parameters, we see that it decreases with age. Sorry?
120, will she speak without moving her jaw?
Sorry? That's a good question. We'll see.
She will not speak.
Yeah. And we see for standard deviation, we also observe that it's decreasing over age, which is also, well, we can expect that maybe she doesn't, it goes together with, well, just shows that the amplitude is less important, so more centralized articulation. So we see that for some of the parameters, and actually, well, we can also just extract one word to see if we see the same effect. And actually, for example, here it's on the word Christmas for the queen, because it's a word that she says most. She say, apparently, you can see every cross here. She says it about 80 times. And we see a similar trends. P1 is also increasing. And what would be interesting is also to see if we see this same trend for different speakers. So this is a database that we used of Spanish speakers. So it's really independent of the language and of the channel because it's a completely different channel and completely different speakers. It's not even English, so it's really Spanish. And we can see that for each speaker, so every line represents a speaker. And we can see that for most speakers, so we have several recordings for each speaker. Sometimes it's only 3 or 4, but over different years. And we can see that for almost every speaker, we see the similar trend that P1 is increasing. So apparently, and this is actually one of the common, so for some of the articulatory parameters, we observe that there is a strong correlation with age. You can observe a very common trend that we observe for, well, we still have to do this experiment for many different speakers, just to check that we find the same tendency. And so the most consistent result is a decrease in the amplitude of the articulatory movement, because I only show P1, but for some of the articulatory parameters, we always see this decrease in the amplitude. Actually, so P1 is the clearest, and then the articulators, the parameters of the jaw, of the tongue, don't change too much. So basically, they keep the same amplitude, but the parameters for the lips are decreasing, and the larynx doesn't change. Actually, that was the most disappointing findings, probably, is that we didn't observe anything about the larynx, but apparently the height of the larynx was always at the same average position. Well, not at the same, but we didn't see any trend. We didn't see it we would have expected to have lengthening of the larynx, but we didn't observe that. And, well, as these parameters are derived from the formant frequency, we have to make sure that when we extract the formant frequency, we don't make a mistake that are biased with age. Otherwise, all the findings that we found would be, well, just something that is due to some automatic extraction problem. And Eva will talk about that. If you have any questions.
All right, good morning, everybody. I hope the microphone is okay. Good. As Blaise already mentioned it, we are working a lot with formant frequencies, which are only 3 values per time frame. So it's, yeah, if you get those wrong, you're really bad off. And so we just wanted to make sure that the whole group or all the members that are using these values know about the quality of the formant values they do their analyses on. So the motivation behind the aspect I'm presenting today is how well is the quality if you take F1, F2, F3 and put them into more refined analysis, as we will hear later on in the talks. And not only are we using the formant frequencies for the vocal tract inversion, but also for age classification experiments. So one way of using them is to have them as input to calculate Maeda parameters, and then the other one is to take them directly. So I'm kind of at the point of, like, the transition point between basic information and experiment information input. And we'll see that automatic formant extraction, the one we are using, is prone to have errors in them. And we'll concentrate on coarse errors, and I'll just mention fine errors on the way along. And what we're interested in is finding out whether the algorithms are biased to age, because that will mean that we have some skewed results. So formants actually, as we heard, they determine the articulation, or they are a means of displaying how we articulate. And this is just a positive example. So here we see F1, F2, F3, and F4 as lines which mark the transition between 2 vowels, making a diphthong. And usually what the algorithm does, it smoothes the line to a nice trajectory. And then you have higher, you get the average of where the energy is highest at each formant. We don't want to have glottis information in there, but we can't avoid having it. So this is just some illustration that the fundamental frequency, which we heard about in Andrew's and Georg's talk, is influencing the transfer function of the vocal tract. So wherever you have harmonics, you have more energy in a theoretically perfect excitation signal. And if you put the filter of the vocal tract on that, you get different values depending on where the harmonics of the F0 are. But this is kind of below the resolution of our analysis, but we still have to keep that in mind. The most interesting thing is shown here, where we have the same vowel twice on the left and the right side. And one of the instances shows a good example of the tracking algorithms where F1 and F2 were tracked correctly as being very low for U. And the other one shows that it's pretty off because it just thought F3 was F2. And that's where we get our errors in the analyses when we take these formants. So what we did was we took a subset of our Queen data and annotated that with background knowledge from phonetics and forced time alignment to see what she was saying, the symbols of the phones. And we also had F0 tracking to know how high her pitch was, and also listen to the speech signal. And we didn't look at the whole signal because it doesn't make sense to look at consonants that don't have any voicing. It's just mainly for the vowels. And we smoothed the vowels to the right, the formant values to the right position to then have this correction in the coarse errors. In total, we annotated about 5% of the data set with a quite high real-time factor of about, like, you take 30 seconds of speech and it takes more than an hour to annotate it. So we just had to restrict ourselves. And then we had 2 algorithms that did automatic extraction, WaveSurfer and WinSnori. And they also gave the same values, obviously. So we determined for each frame of the subset we annotated how they differed from the manual annotation. Calculating root mean, square, median, and standard deviation. And we also counted if the offset was larger than plus minus 32 hertz around some, like the target value of the manual annotation. And the interesting thing was the systematic change over age. And the results show that you can see here, left top is the F1, then right top is F2, and bottom is F3. And this is for one of the algorithms. So what you can see here is the difference in hertz between the manual annotation and the value that came from one of the algorithms. If you have a value of 200 here, it means that the manual annotation for F1 suggested something like 600 hertz, and the automatic extraction suggested something like 400 hertz. So you're off by 200. And the important thing that we want, that we're interested in here is how is the development over age. And you can see we took different, like, over all decades we took some samples. And the lines don't deviate too much from each other, which means that the changes over age don't come into play so much. Yes, Sanjeev?
I want to understand the plot. So when you say difference in age, let's say I pick a positive number like plus 400 hertz. That means that the estimated F3 is 400 hertz higher than the correct F3?
If you're on the positive axis, it means, yeah, that the... No, that is underestimating, actually.
So the estimated F3 is lower than the actual F3.
And by estimating means automatically extracted.
Yeah, that's what the automatically extracted F3 is 400 hertz lower than the true F3.
Right.
So the true F3 was actually much higher, but you found something lower.
Right.
So I'm thinking in the older recordings, could it be because the higher frequencies have been cut off, and so you don't find the F3 where it is, and you find something else lower?
I was just going to go into that.
Okay.
The main thing we can read from these graphs is that the F1 is doing pretty well. F2 is spraying out a little more, and for F3 we have this not working. We have this noise in the upper part. I guess that was what you were getting at. This just means that we do have some noise in the F3, which is in a higher region in the spectrum, and one explanation could be that like the red line is the oldest recording in here, and it has, the highest offset or the highest difference. And we found that the speech signal from older recordings had just a different quality. So sometimes the algorithm did not have enough energy, the spectrogram did not present enough energy for the tracking algorithm to see a formant up there. And so it just went down to the second formant and took that one. So that's something.
Question: why is there a dip at 0? I mean, why aren't there the errors peaked?
Yeah, we decided to take them out because the peak would be very high, just to make it more visible on the edges, on the tails, and we took that out because that was the.
Let's assume that you took out everything between that valley.
Plus minus 32 hertz.
Right. Okay.
Yeah. So that's the highest peak, which means like most of the times they were actually right.
So Eva, if you didn't take that out of your data, but you kept your y-axis range as 0 to 0.14 as it is right now, then these curves would sort of hit the top of the curve and be gone, and you wouldn't see them.
Yeah, exactly. So this is like a zoomed-in version.
It might be better to just present that and put it in the report, because as Salim says, it looks funny to see that nothing has a small error.
So we have this background knowledge to go on, like use the formant extraction algorithms we are using, which is good because we are looking for robust features. So we don't want to hand annotate anymore. And one application to this, one first application was how do the formant values change over age? And this is just a short plot, a quick plot about F1, and you have the age on the y-axis, and you can see how F1 decreases, and it has a pretty good correlation with age. We found something similar for F2, and no correlation, not really, for F3. That's good. Yes. Oh, and
one quick question: how many points per age are we talking about here?
A lot. I mean, that's a good question because we took all the voice segments of each year, so it's basically everything that's voiced.
So about 5 minutes, so 5 minutes of speech, and let's say that of that 2 minutes are voiced.
Right.
So it's 2 minutes of speech for every age point. So there are 30 age points, and for each there is about 2 minutes of speech.
Yeah, about that, yeah.
So each vertical red bar, for example, is basically
12,000 frames.
Yeah.
Yeah, a lot of data. So this was just the first step into results on age, and we'll go on with
you have the phonetic transcription of what they said, or what she said rather. Did you try to look based on your phone if things change?
Can you just pick a particular vowel, let's say pick E's or R or something, and look at all the R's?
Right.
Would that make that?
Yeah, that's actually reflected. So this is just a more more easy overview of everything, but it's reflected in the single vowels. We had another experiment on that.
So the correlation is just as good or as bad? And it's phonetic dependent?
Well, you have the problem that any labeling you have, any transcription, is always cannot be very exact. So you'd always have reduced vowels, which mess up the picture. But if you take only the clear instances of a single vowel, then you get the same. Might be a bit better, but the tendency is the same. So that's what we are looking for.
So some of this variation is because there are different vowels mixed in here whose natural F1 would be different.
Right.
And then some of it is because even for a given vowel, sometimes it is clearly articulated, sometimes it's reduced, and sometimes the context might do something to it.
What are the error bars there?
That's the standard deviation. And that's so high because we put all voice segments into one. So F1 for E is in there, and F1 for A as well, so you get high differences.
Okay, good morning. So as Eva told us, there is no systematic error over age for the formant values. So we take those formant values for further analysis. And so in this talk, I will mainly talk about some of the acoustic features to see if they change over age. And then, so mainly my focus will be on speaking rate and duration of transitions and pauses. And then Werner will continue with other acoustic features. So we did some duration experiments on the Queen data and University of Florida data. The input we used was forced time alignment, and we used formants as well for this data set. And the experiments we did were speaking rate and then duration of plosive vowel and pause percentage. Okay, so how do we define speaking rate? The speaking rate is number of phones per second, and then this is the plot for University of Florida males database. and the x-axis is age and y-axis is number of phones per second. And we can see a nice trend here that the speaking rate decreases over age. Okay, so
But did you count something different? Maybe count the number of syllables per second or something like that?
so number of phones per second, but I excluded silences and pauses.
Okay. No, what I'm thinking is, well, I mean, it should be very strongly correlated, but
it's highly correlated.
Mm-hmm.
But we would have had to segment it into the syllables.
Right, okay. Or you could just count the vowels and liquids or something as a substitute for counting.
It's highly correlated. We did that on German data before. I mean, I did it.
Okay.
Okay. So then this is something interesting that we found that for the queen, speaking rate first, so when she was young, the speaking rate is really low. When she is middle-aged, it is very high, and then afterwards it again she again gets lower. So then you can see and then we think that the first change, like this change, that might be because of the professionalism, but then this might be because of the aging. Okay. Then the other experiment we did was for plosive vowel transition, and so this is some formal definition for plosive vowel transition, and let me explain you quickly that, okay, so the thing is, like, whenever there is a plosive and a vowel followed by a plosive, it takes time for the articulation of that vowel after the plosive. So for example, we have plosive g here and a, vowel a here, and this is end of plosive, end of the plosive, and then the actual vowel a starts here. So these lines so these are formant frequencies for a. This is F1 and F2, and the actual vowel starts at these points, and we define this as the transition duration. Okay, and so the hypothesis is that the transition duration gets longer and longer as the person grows older. Okay, so then we looked at plosive vowel transition durations, but then we observed that for individual plosive vowel pairs, there is not actually a good trend. So what we did is we made classes of some plosive vowel, and then this is a plot which shows that, okay, so this is the plot for University of Florida males data, and then so we can see a slight trend here that the transition duration so transition duration increases over age, and then we can also see that there is slight increase in variability as the person gets older. Okay, and then this is the plot for plosive vowel transition for the queen, and we can see very slight trend here, but the thing is the variability, it decreases over age. Okay, and I mean, of course we know that these plosive vowel, so we don't have anything conclusive about plosive vowel transition duration because, I mean, considering there is some error in time alignment and with informant values as well, and actually it's a very hard problem to exactly know what is the transition point. So we don't have very conclusive results, but still there is a slight trend for a certain phonetic context. Then the next experiment we did was pause percentage, and so this is the plot for University of Florida males data. And then how do we define pause percentage is the percentage of pauses in the whole utterance, and then again here we can see some slight increase in pause percentage for University of Florida male data. We observed the same thing for female data as well. And then, okay, so this is the table for the conclusion. And what we observed was speaking rate shows really good correlation with age, And then so we use that as a feature for age regression. Then pause percentage, so there was, for the queen, there was first decrease and then slight increase, which is consistent with the speaking rate for the queen. So that is, for the longitudinal data, the U shape is always there. And then for plausi-vowel duration, we conclude that more investigation is needed. Okay, so that's it. So now I will introduce Werner for the next talk.
Okay, good morning everybody. My name is Werner Spiegel and I show you now a little more other features we discovered and analyzed in our talk. You heard about the Maeda parameters, about the glottis parameters. Now what I talk, a little more basic features everybody knows and prosodic features, and after that I explain a little experiment we did with all these experiments and a special feature analysis, and after then the support vector regression. So the basic features everybody knows are the MFCCs. MFCCs are good for everything, so we use it. Why not? We tried. So we have a 24-dimensional feature vector, static and dynamic features on the MFCCs. And we have, what we also use are the formants. You heard in the talk of Blaise that the formants are the basis for creating and estimating the Maeda parameters. So why shouldn't we use the formants also as features? We extracted, as Varada and Eva said, the formants with WaveServer. Another well-known basic feature is the F0. We took, everybody in the whole workshop group knows this picture of the queen, the F0, and it goes the same way as in the literature. We can hear the voice.
It is 2 years since my husband and I spent Christmas with our children. As I look back over these past 12 months, I know that it has been about as full a year as I can remember.
Yeah, there's an obvious trend we could see in the data, in the average F0. Also, we can see for a female, for Alistair Cook, a trend down to 75 years and then up again. So let's hear it.
Good evening. In the year after the dropping of the first atomic bomb, it's very hard to pretend that the new year is the turning point of anything very serious.
Good morning. Here is a little exchange of dialogue from an English novel written in 1915.
Yeah, we have nice correlations here in the F0, in the mean F0 over the year. So we take it as a promising feature for speaker-dependent analysis. You know, we have the one data set of Alistair Cook and Queen. We can run speaker-dependent experiments. And we have the cross-sectional data of the Florida. So, and we did also the extraction of the F0 and averaged over a year. And what we see here is not so obvious trend. So, yeah, but if we cluster here in the younger part, older part, middle part, and older part, yeah, we can see a trend. So more data, then we can define this trend again for the cross-sectional data. Let's go to the next feature set we used, the prosodic features. What is prosody? If somebody talks about a prosody of utterance, then normally it means we talk about how the utterance was presented. So prosody is just a cover term for the dynamic in speech phenomena. They are larger than phonemes or frames. So we can't describe dynamics in the speech just with a frame or a phoneme. We have to look at a larger segment. So what we hear is pitch, loudness, speech rate, and rhythm. Yeah. And how could we use now the prosody in the vocal aging problem? Yeah. The interesting thing in the vocal aging is not the change in the place of the articulator. So the vocal tract increases or so. The main important thing is the change in the dynamics of the articulators. So with a prosody, maybe in emotional detection, we have a short term, and now we just have to scale it into long term, and we can use the prosody for our vocal aging problem. So the idea is prosodic features cover the dynamic of changes of vocal aging. The first prosodic feature I present you is the jitter and shimmer. I think everybody knows what it is, just a short reminder. The jitter are just the irregularities in the pitch period, and the shimmer irregularities in the energy of the pitch. Here again a plot of the average pitch of Alistair Cook. There's also a nice trend. Yeah, again in the speaker dependent and longitudinal data we see here.
What are the units of this on the y-axis? I don't understand the number, just explain it to me.
Yeah, these are just numbers. We can compare. It's the number we...
the standard deviation divided by the mean or something? Or?
It depends on how we extract the jitter.
Okay.
The jitter is actually extracted directly on the periods here. We extract the periods, and after then we have a lot. We count this. We draw this in a line, yeah. And over this we interpolate. And the error to this interpolation line we calculate. It's a residue, okay. And the difference of this preceding and of residue 0 and the preceding, this gives us this number.
Okay. So in other words, if the pitch was constant, then all these lines would be on the horizontal, all these points would be on the horizontal line.
And if the pitch
was rising steadily,
it's also, yeah.
So this is deviation from straight line variation of pitch.
But it takes away a little bit the effect of a rising pitch, right. Because you don't want the rising pitch to attribute to have in the jitter.
In other words, if you're going to vary pitch, vary it along linearly,
right.
Piecewise
exactly.
linear segments, and then
you look at the intrinsic variation there.
Okay.
Yeah, and now we go in the part of the prosodic features. We go to the structural parameters. You know, we can use any phonemes or frames or so. We have to use larger segments. And in our approach, we used for the segments the voice segments. We used to calculating these segments the F0 and the energy. And in these voice segments, I show you for illustration a picture. Here's the timeline. Here is the value line. Just imagine the F0. And now what we try is, in this voiced part, to extract objective values, like the maximum of the F0 in this voiced part, the minimum. We draw a regression line. We take the positions of all these parameters and take it as features. And after that, we have these numbers and a lot more. We take not only one segment, we take up to 5 segments together to cover the dynamic features. So what we have now, we have a lot of features we can just put together and run an experiment on age regression. And the main motivation for the first experiment is, don't focus on the speakers, just focus on the age. So we have the Florida data, and we take of every year, of every age, the speakers into one utterance. So every 28-year-old into one utterance, 30-year-old, and so on. So out of the 150 speakers of our data set, we get 78 concatenated utterances. We extracted our features of of these utterances, F0, F1 to 3, prosodic, Maeda parameters, glottal parameters, and so on. And we calculated the means and the standard deviation over this and combined it to a big vector of each utterance. So we had 39 utterance and 39 feature vectors per gender. So, and what we did with this, just a closer look into the features. I correlated the features with the age. Each feature in this 465. And the first features for males and females I show you here. These are the prosodic features. I don't go into detail, but you can see for the males, at least one feature is enough for a 0.8 correlation, but it's Pearson correlation. There's everything in it. And for the females, we have a F0 prosodic feature with 0.69. After this analysis, we took this large feature vector and put it into a support vector regression just with a linear kernel because we are in a high dimensional space and we only have 39 instances. And these are the results. So the correlation you see here is not the Pearson, it's a 39-fold cross-validation correlation. So the correlation calculated here, it's speaker dependent. So the test is not in the training set as in the Pearson. So we get a 0.9 if you take only the means out of the feature vector and a mean absolute error of 8 years. And for the females, we can go a little bit less in the feature space. This means I took only the features who have a higher absolute correlation than 0.5 to the age. So, and for females, we get a correlation 0.88 and a mean absolute error in years of 9 years. Okay, what we see here in these results is, yeah, we can make it very, very good. But you should keep in mind, we use up to 7 speakers in one sentence. And yeah, in the next section, we will see what happens if you take for test only 1 speaker per year, a reduced feature set, and less time data. And this will present Young. Thank you.
Hi. So I'll talk about, up till now we've seen that there are many features that correlate with age. Right now, I'll look at how well we can do at actually predicting the age using certain features. We created a system, an age prediction system. We used a universal background model and Gaussian mixture model to create age models for each age of the database, and then we used support vector regression to predict the age of a specific speaker. We used various features. We used MFCCs. We used the three formant frequencies, and for some, we also used Maeda parameters for evaluation. We first built a UBM using unsupervised clustering. We used Gaussians to define each cluster, and we started off with 128 random points in this feature space, and we did 20 iterations of expectation maximization algorithm. And then for each age, we did map adaptation using the universal background model to create a model, an age-adapted model for each age.
Yeah, quick question.
Yes.
If your features include the Maeda parameters or the formants, does that mean you're only using sort of the voice segments of the speech?
Yes, for the Maeda parameters and for the formants, we only use the voiced.
So is that the only speech you use? Because if you use the unvoiced one, your vector components will be undefined.
Yes, so we cut off all the unvoiced sections. If you
get a minute of speech, you might only use 25 seconds of it.
Yes, yeah.
In the actual, to sort of model with the GNN.
Yes, yes.
And how is the chopping up done?
We use, if there is no pitch, then we just cut it out.
So if your pitch detector says there's no pitch, you leave
Yeah,
that frame.
we just cut it, yeah.
So any frame that has pitch is in.
Yes.
So you have a variable parameter for age, or you have binned the ages so that you have different?
For the training data, we actually bin the ages, so we have an age, a model for the 26-year-old, a model for the 30-year-old, a model for the 31-year-old, stuff like that.
So how many different models do you have?
It depends. For the Queen data, we have 30 different models. For the Florida data, we have a lot more models.
39.
39. And then we took a test speaker and we extracted features. We also did map adaptation using our previous UVM, and then we fed it to our support vector regression to actually predict the age of the speaker. We looked at different kernels, but the results I'm showing now are with the linear kernel. The other kernels show similar results also. So we first did it on the Queen data and the Alistair Cook data. This was speaker-dependent evaluations. So we did a full 30-fold leave one age out cross-validation, which means we took 29 years from out of the 30, and then we trained on the 29 years. We tested on the remaining 1 year, and we did this 30 times with different years. And we have a nice correlation of 0.95, and with the MFCCs, an error of 4.2 years. And also very similar with the Alistair Cook data. But now this data is this is speaker dependent, and this and channel may have an effect on this data. So we also took the University of Florida data, and we did the same experiment. This time we did it speaker independently, so we had a separate training data, and we have separate test data. So we did it on separate sets, and we also, for females, we had a very high correlation for MSCCs 0.92 with mean absolute error of 9.5 years. For males, we had a bit lower correlation, but we still had a pretty high correlation of 0.77. For the formants, we didn't have a very high correlation, but we think this is due to the fact that for males, there's not much of a difference in formant frequencies as in females. And so we wanted to know how much data we needed to actually, how much data we needed for us to actually predict the age. And we used different lengths of speech to test. And you can see that around 1 minute of speech is enough for us to actually predict the age of a test speaker. And so we compared our results from humans to our system. So this is the humans, which Elmer introduced. This is an average over 40 people. We divided it into 3 age groups. And you can see the confusion matrix here. We have an accuracy of 87% for humans. This is an average over 40 people, and they were 9 years off on average. Our system, we had an accuracy of 76%, and we were 11 years off on average. And that's...
Actually, in the cross-validation result, you said that there is a 1 year out.
Yes.
Cross-validation.
No, this is yeah.
For 30 years, right?
Yes.
Why only 30?
Because the Queen had 30 years. We had data on Queen for 30 years. This is not cross-validation. This is the University of Florida data, which is speaker independent. That's it.
Okay, we'll have 10 minutes break, and then we will continue with the experiments with respect to speech recognition.